All right, everybody, welcome back. This is 3.2 part 2 after you just did this simulation right here. Okay, so these are actually the last questions on your lab, and you should have been able to answer those. Okay, so for example, as the pressure, we're going to say, increases or goes up, the temperature will blank if the volume and the moles are constant. What happens? Well, the temperature also goes up. That's what you should have found. Okay, and there's graphs with that you were making in your lab. As volume, let's just say as volume increases, we'll just stay on the positive. If the volume increases, so the volume gets bigger, pressure will blank if the temperature and the moles are constant or the amount of particles are constant. Okay, so if the volume increases, the pressure will actually go down. Okay, the pressure will actually go down. Okay, as the number of particles or moles, let's say the number of moles or the particles increases, the temperature will do what if the pressure and volume are held constant? And this one's kind of hard. This one's actually kind of hard. The temperature will actually go down. The temperature will actually go down. It's kind of crazy, and we'll talk about that in class. But the idea is because there's more particles and the volume and pressure remains the same, since there are more people, it's like you can't move around as much. Now, as a human, we might think, oh, well, that's bad. We're going to get really, really warm in that room. But that's not what we're talking about. That's ambient heat. We're talking about the speed of the particles. You can't really run across a room if it's a packed room. So your temperature actually goes down if kinetic energy is related to temperature. Alrighty. So hopefully you enjoyed that little simulation. It's pretty easy, and it's a lot of fun, to be honest, to mess around with it. You get to pop the lid off the simulation, and some of you try to break the simulation, and that's okay. That's what science is all about. Okay. So, how does it work? Okay. The whole idea is when that gas expands, it forces molecules to kind of stop doing what they're doing. The kinetic energy increases, and the pressure goes up. So the pressure law is at a constant volume. And so that's what you kind of did without even knowing it, where pressure is equivalent or is directly related to temperature. So if the volume is constant and we increase the pressure, then the temperature is going to go up. So if P goes up, T goes up. If P goes down, T goes down. All right. So there's your pressure laws. Basically, what I just told you. Kind of those are the knowns for it. So if you want to pause and read that, you can. Boyle's law. Boyle's law is constant temperature. Now look, this is actually an inverse or an indirect relationship, okay? Which means if pressure goes up, volume goes down. Or if volume goes up, pressure goes down. So it's an inverse relationship. Where the other one was a direct or a direct relationship, this is more of an inverse relationship. Again, everything we just said right there is written out for you. Pause it. Take a little read if you want. All right. And then Charles or Chuck's law. Constant pressure. Okay. The volume of a fixed mass of a given, or the volume of a fixed mass of gas at a constant pressure is directly proportional to the temperature in Kelvin. So again, if volume increases, okay, if volume increases, then temperature will increase. If volume decreases, then temperature decreases. And that's kind of against what we think, right? Because we think more people in one room, it's going to get hotter. But it's not really talking about that. It's talking about the energy or the ability for the molecules to move. Okay, because we're talking about kinetic energy, not really thermal energy, but kinetic energy. And again, here is your constants or your explanations for those. Take a pause if you want. Come on back. All right. These are assumptions of the kinetic model. And IB, they literally want you to memorize these 6 things, which, again, it's hard to memorize them. But to be honest, if you really read them, they all kind of make sense. You kind of had to make these assumptions anyway. Newton's laws apply. Well, again, we have to follow the laws of motion. No intermolecular forces. It means only interact during the collisions. So gravitation is not part of this. It's not like they're orbiting each other. Molecules are treated as points. Molecules are in random motion. The collisions between each are perfect elastic, which we already talked about. And basically, we're saying there's no impulse. There's no time of change. Okay, there's no Ft equals mv. The momentum exchange is pure and instantaneous. So that leads us all to the ideal gas law that I mentioned way back in part 1, where PV equals nRT. And basically, this is your big equation for this section. The idea that pressure and volume relates to N, which is the number of molecules, okay, almost like Avogadro's number in a way. R, which is a constant, which is given here. And T is temperature in Kelvin. Got a worked out solution for you. Most of you have taken chemistry. You understand how that works. If you need to pause this and look through that, you're more than welcome to do that. But this is about as easy as it gets. Notice that most of the time we put it in kilopascals. Okay, kilopascals. So a lot of times if you got that answer before, it'd be in pascals. So it'd be 1.2 million. Well, we tend to shrink that down a little bit by making it a kilopascal. Okay? And so now we're going to watch this time warp video about dry ice and the idea of pressure and all that stuff squeezing in on itself. So 1 second while I load this up. Here we go.
Other ways that ordinary household items can explode. And by ordinary, we mean ordinary.
If you've ever seen a Halloween punch bowl before, you're looking at the delightful mist of dry ice.
Cool. Usually we slow things down, but in this case we're speeding things up. Note the ice cube on the left melts into a puddle of water. The dry ice on the right evaporates into thin air. But what if that dry ice had no place to go? Say it was trapped inside a bottle.
The dry ice is just solid carbon dioxide. It freezes at about 107 degrees below 0 Fahrenheit. Now that water is at room temperature. That's almost 200 degrees difference from the dry ice. Right? So it melts really quickly, but carbon dioxide skips the liquid and goes directly to a gas. Because it skips liquid, it can have extremely explosive results.
Now I know what you're thinking. Why is Jeff cutting up pieces of dry ice on a bandsaw? 3 reasons. 1, preparing for an illuminating scientific demonstration. 2nd, dry ice can and will burn your fingers. And 3rd, an extra lean cut of dry ice is easier to cram inside a bottle.
As soon as this converts to gas, it wants to take up about 1,000 times the volume that it currently is. And so we're going to fill about half of this, but it's going to want to be 500 times the size of one of these bottles. You can guess what's going to happen then.
Yeah, I think we're going to have one of our patented kabooms.
Well, we like kabooms, right? So it will probably go kaboom.
Matt and his high-speed cameras are now set up to capture every millisecond of explosive force from the bottle as the carbon dioxide gas expands.
We've got eye protection already. I think we're good to go. I'm just going to add some hot water to accelerate the reaction.
I'm going to accelerate my exit. So when you cover this, we leave.
Ignition.
Ready?
Yep.
Countdown.
Goodbye. Yeah. Well, it's going to happen.
Did we mention this could just be a theory?
No! No! All right, well, I hope you got that.
The triggers were set. We should have it. I just have to restart my art first.
After an onset defib, we played back our footage at 5,000 frames per second.
Wow. Even that is so fast. That's less than 1,000th of a second.
It literally propelled right at where we were.
Yeah, that whole thing took less than 100th of a second for it to move several feet. That thing is going amazingly fast.
Now we're showing you this a few times so you know what it looks like, so you never ever feel like trying it yourself. Dry ice or not, this is a real explosion and not something anyone should mess with. Just how destructive this can be is demonstrated by our next experiment.
We're going to do 3 bottles now. We're going to take it up about 5 notches right now. We're going to put 3 bottles in the water. They're going to be surrounded by a ton of pressure.
So essentially, we're making a dry ice depth charge here.
I would say that's exactly what we're doing.
Pop it in.
Pull that guy down.
All right. I'm out of here. Come on.
Much higher. That's good.
And what's going to happen?
Well, what's going to happen? Obviously, they would naturally explode at different times, right? However, Those are so close together that once one of them creates that pressure wave, it's going to definitely cascade to all three. There's no bubbles escaping. So this thing is building up pressure. This could be bad. Let's give a...
I command you.
Oh,
Starting to expand.
oh my God.
Okay.
Okay,
The cameras.
Cameras are okay. Very good.
Real smart guys. Only one bottle burst, and the other two are sitting in the middle of our extremely expensive equipment.
Wait a second. Has that gone?
No, I don't know.
Those guys are I don't think those have gone yet. So keep some distance. Let's set those off manually. There's the other one is live as well. What? I want to do it. If anyone has any problem with this, speak up now.
See why nobody should try this at home?
That tank is 1/8-inch thick steel. There's no way you can bend that with your hands, and that thing looks like tinfoil.
Thrown around like a rag doll. And essentially, that's one bottle.
It's totally unexpected. I really thought that the first one would definitely trigger the ripping of the other two.
I can't imagine what that would have looked like if all three went at once.
Viewed at 10,000 frames per second. One bottle bomb was plenty, thank you.
That is an amazing shockwave. You can see it starts out pretty asymmetric. It has to move the mass of this thing out of the way. But then it's pretty much a sphere. It's going out as fast as it can. That carbon dioxide wants to expand to something probably the size of a swimming pool.
This demonstrates the law of intended and unintended consequences. Ordinary items, when put together in the wrong way, can become devastating.
This thing is destroyed, man. That is 20 feet away from the tank.
This was here.
So I show you that not so that you'll do it on your own, but I show it to you so that way you know what not to do and that you won't want to do it. And the reason is because it's incredibly dangerous. That was basically bulletproof glass and steel, and it gets launched an incredible distance. So Mr. Tima says, don't do that at home. I won't even do it, so you shouldn't do it. Until next time, guys, I'll see you, Mr.